Okay, so we're going to start talking about vector spaces. So this kind of second half of the course is going to be more kind of theoretical. So I wanted to divide up the first half into a lot of computation, got a little bit more theory maybe on the midterm. The second half, I just want to divide into more theory. So there will still be computations to do, but it's going to be more kind of theory based. So start, I want to talk about set theory first, because when we talk about vector spaces, we will be talking about sets. So I want to kind of give a brief, overview of set theory. So I feel like whenever you talk about set theory, you should always talk about Russell's paradox, which is this. So early on in math, when set theory came to be, the definition of a set, which we'll talk about, is very general. And Russell, as a mathematician, found pretty bad contradiction if you define sets a certain way. So the basis of the contradiction kind of lies in this whole puzzle. So you have the town barber, and they shave all those who do not shave themselves. So the question is, who shaves the barber? So just kind of give an example. Let's say Bob shaves himself. Does the barber shave Bob? No. So barber does not shave Bob. Let's say John shaves himself. Does the barber, does not shave himself? Does the barber shave John? Yes. Barber shaves John. Okay, so the question is, who shaves the barber?
My man's actually doing work here. What is this? Russell's paradox. The town shaves. What's happening here, bro?
Okay, so let's say he does shave himself. Let's say barber. So case one, barber shaves himself. So what's the consequence? If barber shaves himself, what's the consequence? Based on the definition. Yeah, so if barber shaves himself, barber does not shave himself. Right, so that means this is a contradiction, right? So the only possibility is barber does not shave himself. Therefore, barber does not shave himself. So what's the consequence? If barber does not shave himself, what's the consequence? Based on the definition. He shaves himself. Barber shaves himself. But that's also a contradiction. So this is a paradox. In both cases, barber both shaves and does not shave himself. So there's something that's very wrong here, right? That means how we've set up the statement, there has to be something wrong with it, right? So what is the solution to get around this? Yeah, and that's the idea, is that there has to be a condition. Barber cannot be in his own set. So that's the idea. So, I mean, you don't have to know this. Just, I think it's a cool thing to talk about. When we talk about set theory, I think you should always think about this, because sets, they're very simple, but you do have to be careful with, how you define things. So another way of stating Russell's paradox, another statement. So this less fun statements, more math statement. Let's say let S be a set of sets that do not contain themselves. So then is S and S. So you have a bunch of sets, and what's true about every single set is that they do not contain themselves as an element of the set. So for example, if A is an element of A, then A is not in S. If B is not an element of B, then B is in S. So think of that, this as shaves themselves. Barber does not shave. Does not shave himself. Barber shaves. So the question is, if you have this definition of a set as the set of sets that do not contain themselves, is S in S. So again, this is, does the barber shave himself? So, and we have that paradox, right? If S is not in S, then S is in S. If S is in S, then S is in S. Oh, other way around. If S is in S, then S can't be in S. So does that make sense? Do you see like the parallel between the puzzle and this statement? I like the puzzle version is kind of easier to understand, right? Because it's, but this is the more mathy statement. So what is the consequence? So a set is a collection. This is technically chapter 3, but this stuff about sets is not in chapter 3. This is just supplementary material. You don't have to know this stuff about Russell's paradox, but it's good to talk about. So here's the definition of our set. The set is a collection of objects, but to include for Russell's paradox, where the set is not itself an object. So this is to accounts for Russell's paradox. So this is our definition of set. It's a collection of objects where the set itself is not itself an element. So questions on that definition? So all it is just you have a collection of stuff, but the whole collection itself cannot be part of it. Okay, so let's just kind of give some property, some basic set theory. So I think most of you know this. Union of sets. So A union B is defined by if X is an element of A union B, then what do you know about X? So if you have an X in the union of two sets, what must be true about X? Right, so that means that X is in A, or not both, just or, X is in B. So we have that example, right? We have a Venn diagram. If this is A and this is B, the union is everything. This is A union B. It could be in both. That would mean it's in A or it's in B, right? So or does not mean so it doesn't mean like if X is in A, X is not in B, right? It's not exclusive. So sure, we can say, oh, yeah, I mean, sure. So the mathematical term for or means not one or the other, meaning if it's in one, it's not in the other, but if it's in A or B, then it's in the union. So sure, we can say and or. So when you say or, think of and or. So that's so the other thing we can say is about intersection of sets. That's when we use and. So if we have A intersect B, then if X is in the intersection, what do you know about X? So yeah, so being in the union means it could be in A and not in B, it could be in B, not in A, or it could be in A and B. So it could be in both. That's for union. It could be in both. Right? Do you see the difference? Yeah, so but if it's an intersection, then X is in A and at the same time. X is in B. So when we say and, we mean it needs to be in both. When we say or, it means it has to be in at least one of them. Here, we can maybe that's a better way of saying it. X is in at least one of A or B. Is that a better, more understandable statement? Or? So that's what we mean by or. It's an at least one of A or B. It could be in both, that's fine, but it needs to be at least one of A or B. So the intersection needs to be in both. It needs to be in A and it needs to be in B. So if you have A here, and you have B here, that stuff is A intersection. Okay, questions about union and intersection? Okay. Let's talk about disjoint sets. So A and B are called disjoint. If anyone know what disjoint means? Yeah, separate. So like, what can you say about its elements? It is this idea of separation between the two. So like, how would you describe separate in kind of math terms? Yeah, so that's good. So like, if for every A in A is not in B. Sure. So, or A and B do not share common elements. Does that make sense? They're disjoint if they don't share any common elements. Okay, so what do you know about A intersect B? So if A and B are disjoint, meaning this, they don't share any common elements, what can we say about its intersection? Sure, they're okay, D and E, or it's empty. Right, there's nothing in the intersection. So instead of D and E, we're going to say empty. So for example, here's A, here's B, and there's nothing in the intersection. Okay, so we could define the empty set. So the empty set is the set with no objects. That's all. So there's nothing in the set. That's called the empty set. So one way I like kind of think about the empty set, like how to explain it, is like a museum with no art could still be called a museum. So maybe you have all these rooms that have empty display cases, but there's nothing in any of the display cases, or there's no art in the wall. But there could be a reason why a museum doesn't have art. It just opened up. Maybe a thief took everything, but you might still call it a museum nonetheless. It doesn't suddenly stop being a museum since it doesn't have any art. So it's kind of a way to think about it. Or like if you have like a stamp collection with no stamps, it's intended to be a stamp collection, but you just haven't put any stamps in it yet. So I think the empty set's a bit more philosophical, to kind of understand it, but I like thinking of it as like a museum with no art in it. So So any questions on that, like what empty set is? So that has you that is understand that makes the intersection understandable, right? Or disjoint understandable. If there's no common elements, then the common elements between A and B are nothing. So what do we call nothing? We call it the empty set. Okay. Let's talk about subsets. So we use the symbol, kind of looks like a less than sign. It looks like a kind of like a elongated C with a line underneath. We call it subset. So B is a subset of A if for all B and B, B is also an A. So every element that is B must also be an A. Every thing in B must also be an A. Yes, this is just the symbol for subset. So B is a subset. So that symbol just means subset of. Can someone give me an example of a set and a subset? So this symbol means in, right? So this is an element of. Sure, red cookies and all cookies. So the set of cookies red cookies. Sure, we have natural numbers. And we have the set 1, 2, 3. Sure, rectangles and squares, I like that one. Squares, other way around, right? Rectangles are the bigger one. Rectangle and squares are a type of rectangle. Oh, okay, yeah, so here's the difference between that. So let's say this is A and this is B. So for any element in B, it also exists in A. So because B is inside A, B in B implies B in A. But it's not, the other way around doesn't work. A in A does not imply A in B. Right, but like this element out here doesn't need to be a part of B. Does that make sense? Like Samantha? Yeah, so a lot of questions. So yeah, so here's some statements. Empty set is a subset of everything. That is true. You can think of this as, maybe we'll talk about why that's true. And so, A is a subset of itself. So it could, A could equal B. Oh yeah, so that's exactly this. So it the subset could be itself. So, because that still obeys the definition, right? So like you said, 1, 2, 3. Let's say A is equal to 1, 2, 3. And that's true, right? If 1 is an A, that implies 1 is an A, right? If 2 is an A, implies 2 is an A. 3 is an A, implies 3 is an A, right? So, the subset could be the whole set itself. Okay, so if you don't want that to happen, a proper subset usually say B is the C thing without the line underneath it, A, if for all B and B, B is an A, and B is not equal to A. So if you want subsets to not include the whole set, then you call it a proper subset. So the only subset that's not proper is A. Okay, questions on subsets? So we'll think about some properties of subsets with union and intersection. Okay, so if B is a subset of A, can someone say what B union A is? A, right? Union does not mean like add more, right? If the element's already in the set of A, then you don't include it twice. Yeah, the next answer is B. So B intersection A is equal to B. So if B is a subset of A, then the intersection has to be B. So, I mean, that's kind of clear, right? If B is already if all elements are B are part of A, then the intersection just means everything that's not in B can't be included. And A already contains all elements of B, so that's fine. Okay. How about this? Let's say A intersect B. What is that a subset of? Can you think of a set that is the subset? Sure, A union B. What else is it a subset of? A, yeah, and B. So that's pretty nice. So if you take the intersection, then you're guaranteed a subset. So A intersect B is a subset of A, and A intersect B is a subset of B. Right, so if I trace A, then the green is still within A. So this is why the empty set is a subset of everything. If you have two disjoint sets, then that means that this is a subset of A, subset of B, subset of A union B. So if you do that for any single set, right, you can always find something disjoint. It means the empty set isn't everything. Okay, questions about that? Okay. Oh, one more thing about subsets, complement. So complement, so if B is a subset of A, B complement is defined to be A minus B. Another symbol would be like A with a backslash B. So in other words, B complement is elements in A that are not in B. Questions on that? These mean the same thing. It just means A without B, or A minus B. So here's an example. Let's let A be set of n by n matrices. Let B be non-singular matrices. What is B complement? Singular matrices. Here's a fact. I think it's kind of clear to see. B union B complement, what do you think that is? Oh, why is this true? Okay, so non-singular matrix means has an inverse. Singular means does not have an inverse. So n by n matrices that have inverses are called non-singular. So it's a binary, definition of a matrix of either has an inverse or doesn't have an inverse. Right? There's no middle ground. So the complement of the set of all non-singular matrices, i.e., the complement of the set of invertible matrices, must be the set of non-invertible matrices. So elements in A that are not in B. N by n matrices that are not non-singular, so singular. Is that better? Sure. Okay, here's something about complements. If B is a subset of A, what do you know about B union B complement? Union. Maybe intersection is empty. Well, not B, right? It has to be A. So if you include, so you have elements in B, union with elements that are not in B. So that must include everything, right? Again, this is kind of this binary relation on elements of A. Either you're in B or not in B. So if you put the two together, you make everything. And then, yeah, if you have an intersection between a subset and its complement, well, there's nothing, right? Because you can't both be in B and not in B. So then you have like a paradox, right? So the only possibility is nothing. Okay, any questions about that? Okay. Okay, so that's kind of all about about just sets themselves. So now we're kind of going to be more creative with our sets, and we're going to think about how you can add operations on the set. This is no longer a set, but it is a set with operation. So here's the definition. So a function that inputs elements in S and outputs elements in S is called a closed operation. On S. So by closed, I mean elements cannot escape. Elements in S cannot escape S via the operation. So let's just kind of give an example and a non-example. Okay, so first of all, just another way of saying this is if X is an S, then f of X is an S for all S. Another way, so the thing you can do is it doesn't even have to be one element, maybe the function is on two elements. You take a pair of elements and the function on the pair is still an element of S. That could be a function on three elements. Etc. So here's an example. Squaring. Squaring on the set integers. So sometimes I'll use this kind of Z kind of with a line through it as a set of integers. And I always forget the word, but this comes from some German word for integer. It starts with a Z. Can someone explain why squaring an integer is a closed operation? So it's a function that inputs elements in the set and outputs elements in the set, right? If you take, so first of all, the function is you input n and you output n squared, right? N squared is always an integer. So yes, squaring is closed on integers. Does that make sense, everyone? Okay, let's do another one. Square rooting on integers. No. Yeah, well, division is not, yeah, we'll talk about division, but division would not be valid, yeah. Well, yeah, we'll do that next. So square rooting is no, because if you have f of n is equal to square root of n, square root of n is not guaranteed to be an integer. Good. Yeah, so let's talk about division. So division is actually two variables, right? It's f, you input two things. You take x, y, and you output x divided by y. Yeah, so why is division not a valid operation in integers? Right, because you could have like f of 1, 2 is equal to 1/2 is not an integer. So division is not closed. Multiplication is fine though, right? Why is multiplication fine? Yeah, xy is always an integer. How about this one? Let's take f of x1, x2 to xn. Let's make this equal to x1 plus x2 plus xn divided by n on rational numbers. Is that a valid operation? Yes. Anyone know what this function is called? It's an average, right? I take the sum of the numbers and divide it by the amount of numbers. That's average. So that's fine under rational numbers, but not on integers. Okay, so any questions on closed operations? We can even do one more, actually. Let's take non-singular matrices. And let's let our function be the plus function. Is this closed? For non-singular matrices? Not necessarily, yeah. Why not? Can you it's going to be no. Can you come up with an example where A and B are non-singular, but A plus B is singular? Exactly. You could have I plus negative I is equal to 0. Yeah. I is obviously non-singular, so is negative I. And if you add them up, you get 0, which is singular. So the sum is not a valid closed operation. How about multiplication? Is that a closed operation under non-singular matrices? I should say give a specific dimension, right? Because it wouldn't work for different dimensions. How about non-singular matrices? When you take the product. What do you think? Yes or no? Should be good. It is. It's good. Why is that? Because we know that the determinant of AB, so we did last time, is equal to determinant of A times determinant of B, right? If neither of these are 0, then this can't be 0. So if the term is not 0, then it's non-singular. Okay, questions on closed operations? Okay, so let's talk about specific types of operations. Unary operations. So this is one input. So unary operations are the ones that we're like more familiar with, like f of x is equal to x plus 1, that's unary. F of x is equal to x squared. F of x is equal to e dx. All these things are unary. If you want to give something that's more not necessarily mathy, you have a set of colors. And maybe your function is f of color is equal to maybe tinting it. Tint the color by some uniform amount. Right, that's tinting. You add white to it, right? So you're giving this universal function on, you input a color and then you tint the color by some amount. It's a one input function. Does that make sense? Okay. Here's an example of a unary. F of A is equal to A complement. Yeah, sure, that would also be unary. F of x is equal to x squared plus 4x. Yeah, same thing. It's one input and you output one thing. So complement is an example of a unary operation on subsets. All right, so we'll talk about unary operations. All right, so let's do binary operations. We'll kind of use this one the most. So this is functions with two inputs. Can someone give an example of a binary operator? Yeah, the plus function, right? F of xy is equal to x plus y. This is our addition. F of xy is equal to x times y, right? This is our nice multiplication. Maybe we can have something weird like f of xy is equal to x to the y. It's like powering. Example in subsets or sets. F of A, B is equal to A union B. F of A, B is equal to A intersection B. These are example of binary operations. Okay, does that make sense? So literally it's just one put unary, binary is two inputs. So, I mean, you could keep on going, like ternary is function with three inputs. We won't talk about these, but for example, like triangulation. You have 3 points and a function that does the triangulation. Like this would, if this is like x, y, z, this would be f of x, y, z. So there are examples of functions with more than two inputs. For example, that average function that we talked about earlier, somewhere here. This would be a function on n inputs. We're going to focus on just functions with one and functions with two inputs, but just so you know, there are ones with more inputs. Okay, questions on that? Binary, unary, etc. Okay, so let's think about some types. types of unary operations. So idempotent. What's idempotent mean? We should know what this means. A squared is equal to A, right? So in other words, it's like f of x is equal to f of x, right? So if you do a composition, you get f of x back. And what's an example? So it doesn't even have to be matrices. Can you think of an example of something, if you do it twice, it's the same thing as doing it once? So one example I like to use is projection. So if you have a point on the plane, and projection means just like maybe shine a light. You can even, it doesn't have to be like, it could be like a whole object. You shine a light directly onto it, and it casts a shadow. If you do it again, right, the shadow is already on the ground, right? So doing it twice is not going to do anything. Yeah, I'm doing it on the point itself. So projection is xy to x0. So f of, this is as a single point, like the input is xy. It's one input, the point, and that's equal to x0. Yeah, sorry, it's not. How about doing f of xy like that? So it's still one input xy. X negative y would not be idempotent. So if you want to do xy to x negative y, yeah, what is that? Someone say what that is? Oh, no, actually, yeah, that's fine. Yeah, reflections. Yeah, that would also be idempotent. Yeah, good. Right, that's the better example. Xy to x negative y. And if you do it again, you come back. Good. Okay, so that's idempotent. Another example is involution. This came up in a homework. Involution is if you have, first of all, does anyone remember what involution meant? If not, it's sadness. It's involutions are if you have f of x, it's equal to x. So it's like functions that are its own inverse are involutions. Oh, I'm sorry. So yeah, reflections would not be, yeah. Reflections are not idempotent. Do you see why? Sorry about that. Not idempotent. Reflections are actually involutions. Right, if you do it, so f of xy is actually equal to xy, right? It's not equal to f of xy. Yes, yeah. So, but it is an involution. So reflections, right? So if I do xy, I go down to x negative y, and I go back up to xy, I go back to my starting point. Here's another one. Can you say why this is true? Why this is an involution? Yeah, involutions are not idempotent. They're a different type of unary operation. Can you prove why these are true involutions? So you do, what's f of x? Sorry, these are separate functions. They're both involutions. Oh, but multiplying by -1 is also an example of an involution. That is an involution. Yeah, so f of x is 1 over x, which is equal to what? X. So that's why it's an involution. G of x is -1 over x. The negatives cancel and you get x back. H, so when you do the negate function is an involution, do h of x, it's equal to h of -x, which is negative x, which is equal to x. Okay. And we have other ones like 1, 0, 0, 0 times 1, 0, 0, 0. It's involution because we get, so that's idempotent. The better one is, sorry, 0, 1, 1, 1. So if you're thinking of this as a function on xy, you get the identity on xy back. Okay, questions on that involution? Just means it's its own inverse. Okay, so let's do some more. Let's do binary, types of binary operations. So we have commutative. So this is f of xy is equal to f of yx. So can someone give me an example of a commutative binary function? Addition, yeah. X plus y is equal to y plus x. Multiplication, right? Xy is equal to yx. Can someone give an example it's not commutative? Sure, division. F of xy is equal to x divided by y. F of yx is equal to y over x. How about anything with matrices? Oh, subtraction, yeah, subtraction. X minus y is not equal to y minus x. How about matrix multiplication? F of AB is equal to AB, but F of BA is equal to BA, right? But those aren't the same. That makes sense? Okay, how about block sum? You can say the answer. Is that commutative? No. Right, because you have A 0, 0, B is not equal to B 0, 0, A. Right, so you said it was commutative. You can change your mind now. So before the it's due. Okay, here's another example. It's not commutative. Powering. So like f of x, y is equal to x to the y, but f of y, x is equal to y to the x. These are not the same. Okay. Let's do associative. So it's going to look funny how I write it, but try to see why it's the same. This is f of x, y, z is equal to f of x, f of y, z. And see why that's our usual associative. Everyone see that? Okay. Give me some examples of associative. So addition, multiplication, how about matrix multiplication? Yes, matrix multiplication. How about block sum? Yeah, good. A plus B plus, should put B in there, right? Plus B plus C is equal to A plus B plus C. The non-associative are the harder ones to think about. I'll give you some examples. For those who have maybe taken a physics course or maybe a Calc 3 course, you might have heard of cross product. That's not associative. But here's kind of a more tangible one, is midpoint. So what is the function of midpoint? Can someone say? How do you find the midpoint between two values? X plus y over 2, yeah. So let's see what, if it were associative, let's kind of say what that would be. So it'd be like f of x, y, z versus f of x, f of y, z. So first, let's say what f of x, y is. We just said it. X plus y over 2. And this is y plus z over 2. So what would the midpoint of this be? So this would be, you take the first, you plus the second, and you divide everything by 2. Yeah, so this is, so is it x plus y over 4 plus z over 2, which is x plus y plus 2z over 4. right? So let's calculate the other side. So what would this be? It would be x plus y plus z over 2 over 2. And then let's say what that is. It's 2x. No, not 2x. It's x over 2 plus y plus z over 4. And we get 2x plus y plus z over 4. Is the left part correct? I think so. Where do you think it's not correct? This thing here? Yeah, so if I'm dividing the whole thing by 2, I can split it up into dividing this by 2 and dividing this by 2. So this gets a divided by 4, and this gets a divided by 2. Oh, the next part, I'm doing common denominator, right? Common denominator is 4. So if I multiply z over 2 by 2 over 2, I get 2z over 4. Right, I get x plus y over 4 plus 2z over 4, and then I combine it. That's okay. So you see, these aren't the same, right? So I mean, it depends on what x and z and r are, right? But so when you take the midpoint of, yeah, so midpoint is not associative. Okay, questions on that? Okay. Let's do some other things. So let's think about special elements in a binary operator or under a binary operator. So this is a identity. So if there exists an element E such that f of x E is equal to x, then E is called a right identity. If same thing, but on the other side, if EX is equal to x, then E is a left identity. And if they're the same, if you have XE equal to x and EX, if they both equal x, then E is just called the identity. So usually we won't care about left versus right, but there are certain cases where it does come into play. So can you give me an example of an identity for some operation? So how about addition? What's the identity for addition? Zero, yeah. How about multiplication? 1. How about matrix multiplication? The identity matrix, I. Now, here's something that's weird about left and right. Let's think about powering. So if f of x, y is equal to x to the y. Can someone give an identity? 1, yeah. Y equals 1. What kind of identity is it? It's only true when y is in the second, when 1 is in the second position. Yeah, is a right identity. But it's not true the other way around, right? So f of x1 is equal to x to the 1 is equal to x, but f of 1x is equal to 1 to the x, which is not equal to x, right? So 1 is a right identity, but not a left identity. So there are some cases where you do care about right and left, but we usually won't be thinking about that. So for example, powering has right identities, but the left identity is kind of specific for the value. I mean, if you want to think about it, if you have ax, I'll let you kind of figure this out, but a is actually equal to e to the ln of x over x. So you can work that out if you want, but you don't have to do that. Okay. Let's do, and then inverse. Okay, so this is called, so it's a right inverse. If f of x, x inverse is equal to the identity. It's left if that's equal to identity, and then it's just the inverse if it's inverse on both sides. So let's just do an example. Additive inverse is the negative x. The multiplicative inverse is 1 over x. Matrix inverse, it's, right, it depends on the matrix, but it's A inverse. Do integers have multiplication inverses? So within the set of integers, do there exist inverses? Yes or no? It's the last thing, then we're done. We're at 8:15. Okay, well, what's an example? What's the inverse of 2? Sorry, you're right, multiplicative inverses, I meant. Yeah, it would be 1/2, right? But 1/2 is not an integer. So within the set of integers, no integer has a multiplicative inverse that is also in the set. So it's not like closed under inverses. So, okay, so next time we'll talk about specific types of sets that have certain operations. So for example, there's things called groups, rings, fields. We will be focusing on fields. And there's also, with fields, along with fields, we'll talk about something called scalar multiplication. And then we'll lead into vector spaces. So vector space is a type of set with some operations. Okay, so I'll see you Wednesday. I'm actually being observed on Wednesday, so your best behavior. But okay, I'll see you Wednesday. Good luck with the rest of the midterm. Hope it works out, and I'll see you Wednesday. Oh, you have something to ask? Sure. You can private message me if you want. Yeah, you're every class is you guys have been fun. What total points? I haven't decided, just because I kind of want to see how people do on certain problems. Like if there's one problem that like y'all just miss the point, then I might kind of drop that problem. It depends. I'll probably weight the harder problems a little less because it'll be more tricky. But pretty even per every problem. I'll kind of like divide out evenly. But I mean, if I see a good effort, you know, and you answer most of the problems, you know, and it's all your own work, nothing from online, then you'll get a good grade. But if it's you like don't do anything, or if it's very clear that you just copied from somewhere, then it's a different story. Yeah, I can stick around for midterm questions if you have, or things that we did today. Let me know. If not, I'll head out. Oh yeah, I need to stop recording.